What if one of the best chances of finding alien life isn't on a distant exoplanet light years away, but right here in our own solar system, locked beneath the frozen skin of Jupiter's icy moon, Europa? For decades, scientists have suspected that beneath Europa's cracked, gleaming crust lies a vast ocean, possibly more water than all of Earth's seas combined. But water alone isn't enough. To be truly habitable, that ocean needs the right chemistry. And now the James Webb Space Telescope, humanity's most powerful cosmic eye, has delivered a discovery that changes everything. In this video, we'll explore what Webb found on Europa, why it matters, and how it brings us closer than ever to answering one of the greatest questions of all time: are we alone in the universe? From Europa's chaotic terrains to its mysterious hidden ocean, we'll journey through the science, the mystery, and the staggering implications of Webb's findings. If you love diving into cosmic mysteries like this, don't forget to subscribe and check out our other videos. The universe has many more secrets waiting to be uncovered. For centuries, Jupiter has loomed in our skies like a gas giant king, a world of storms, lightning, and bands of endless clouds. But the true secret of Jupiter may not lie in the planet itself, but in the icy worlds that orbit it. Among them, one moon shines brighter than the rest: Europa. Europa is no ordinary moon. Slightly smaller than our own, it glows with an almost deceptive serenity, its surface gleaming like polished marble, streaked with long, rust-colored scars that run for thousands of kilometers. But beneath that frozen skin lies one of the most tantalizing mysteries in planetary science: a vast global ocean locked away beneath kilometers of ice. To scientists, Europa has always been more than a moon. It is a potential habitat, a place where the conditions for life may exist not on the surface, but deep within, under crushing layers of ice, in an alien ocean untouched for billions of years. The question is simple and yet profound: could something swim in those waters? The first hints of Europa's strangeness came in the late 1970s, when NASA's Voyager probes swept past Jupiter. The spacecraft sent back images unlike anything astronomers had seen before. Instead of craters and mountains like Earth's moon, Europa's face was smooth, as though constantly resurfaced. Great cracks sliced across its shell like fractures in stained glass. The lack of impact scars told scientists something astonishing. Europa was geologically active. Something, perhaps tides raised by Jupiter's immense gravity, was reshaping this frozen world. Later, in the 1990s, the Galileo spacecraft orbited Jupiter and revealed even more. Its instruments detected a magnetic signature that hinted at something conductive beneath the ice. The best explanation? A salty liquid ocean. Suddenly, Europa was transformed in the eyes of science, not just another frozen ball, but an ocean world, hid in more water than all of Earth's oceans combined. Water is life's solvent. Wherever we find liquid water on Earth, from the depths of the oceans to boiling hot springs, even beneath glaciers in Antarctica, we find life. Extremophiles, bacteria, and strange organisms thrive in conditions once thought impossible. So if Europa has water, does it also have the potential for life? This possibility turned Europa into one of the prime targets in the search for extraterrestrial biology. More than Mars, more than Titan, Europa became the icy beacon calling scientists to wonder if we might not be alone. Because if life could emerge in the cold, dark seas of a moon hundreds of millions of kilometers away, then life might be everywhere. But Europa's secrets are locked away. Its ocean is buried under a shell of ice, perhaps 15 to 25 kilometers thick in places. Imagine standing on that surface. Beneath your boots, ice older than human civilization, and far below, a hidden sea stretching for thousands of kilometers. No sunlight reaches that ocean. Instead, it would be heated by tidal flexing, the constant gravitational kneading by Jupiter and its fellow moons. This process may power hydrothermal vents on Europa's seafloor, much like the ones on Earth where life first may have begun. Scientists imagine Europa's ocean as a place of constant darkness, warmed from within, salted and rich with chemicals churned up from the rocky mantle. If these vents exist, they could spew minerals and energy into the water, providing the raw materials life needs. The question isn't only whether water is present, but whether it is connected to the surface, because only then can instruments like the James Webb Space Telescope detect its chemistry. Think of Europa as a cosmic puzzle box. Each piece of evidence, the cracks in its crust, the magnetic anomalies, the hints of plumes, offers a fragment of the bigger picture. But opening this box is no easy task. Probes cannot simply drill through kilometers of ice. Until future missions can land, scientists must rely on telescopes orbiting Earth, spacecraft flybys, and careful analysis of the faintest signals reflected from Europa's surface. This is where the James Webb Space Telescope enters the story. Unlike any observatory before it, Webb can see in the infrared, the light invisible to human eyes, the glow of heat, the spectral fingerprints of molecules. This ability allows it to study Europa in a way that Hubble never could, not just to image its surface, but to analyze what its ice is made of and whether any signs of chemistry connected to life might be present. Why does it matter what Webb finds on Europa? Because each discovery reshapes our sense of place in the universe. If Europa's ocean contains not just water but carbon, salts and chemical energy, then it checks off almost every box we associate with habitability. In a way, Webb's observations are the first scientific taste of Europa's hidden sea, but the stakes are even greater. Finding the right chemistry on Europa does not prove life exists, but it strengthens the case. And if even one moon in our solar system harbors biology, then the universe is likely full of life. As Carl Sagan once put it, if we are alone in the universe, it sure seems like an awful waste of space. Europa, silent and frozen, might one day prove him right. Europa has seeped into our imagination, not just as a scientific curiosity, but as a canvas for speculation. Arthur C. Clarke famously wrote in 2010, Odyssey 2, about the warning, "All these worlds are yours except Europa, attempt no landing there." He imagined Europa as a cradle for alien life, too precious to disturb. For decades, fiction has echoed what science suspects, that beneath its ice, something extraordinary may stir. And now, with the James Webb Space Telescope turning its golden mirrors toward Jupiter's icy moon, that fiction edges closer to fact. What Webb has uncovered on Europa is both thrilling and sobering. It reminds us that while we may be on the brink of discovery, we are still outsiders, staring at a world of oceans through cracks in the ice, desperate for a glimpse inside. To understand how Webb could even attempt such a feat, we must step back and see the telescope itself for what it is. When the first images of Europa reached Earth in the late 20th century, they were astonishing, but limited. Scientists could see the cracks, the chaos terrain, the mysterious smoothness of its surface, but they could not pierce its icy veil. Something more powerful was needed, a tool capable not just of looking at Europa, but of listening to the whispers of its molecules. That tool would take decades to design, test, and finally launch: the James Webb Space Telescope. The story of Webb began in the 1990s, born from both inspiration and necessity. The Hubble Space Telescope, launched in 1990, had transformed astronomy, delivering breathtaking images of galaxies, nebulae, and distant stars. It showed us the universe in a way no one had seen before. Yet for all its brilliance, Hubble was not enough. Hubble's 2.4-meter mirror was powerful, but its sensitivity was strongest in visible and ultraviolet light. Many of the universe's secrets, however, from the first galaxies to the atmospheres of distant exoplanets, shine brightest in infrared light. Infrared is the glow of heat, the radiation emitted by cool objects invisible to the naked eye. To truly explore the cosmos, scientists needed a telescope that could see in the infrared with unprecedented clarity. Thus, the vision of a next-generation space telescope was born, one that would look back to the dawn of galaxies, peer into star-forming clouds, and closer to home, examine worlds like Europa in exquisite detail. To achieve this vision, the new telescope would need to be far more ambitious than Hubble. The mirror. Webb's primary mirror measures 6.5 meters across, nearly 3 times the size of Hubble's. Too large to fit in any rocket, it had to be built in 18 hexagonal segments that would fold up like a puzzle during launch, then unfold flawlessly in space. Each segment is coated in a microscopically thin layer of gold, chosen not for its beauty, but for its ability to reflect infrared light with maximum efficiency. the sun shield. To see faint heat from distant worlds, Webb itself had to be kept colder than anything it observed. Infrared detectors are so sensitive that even the telescope's own warmth could overwhelm them. The solution was a 5-layer sun shield the size of a tennis court, made of ultra-thin Kapton film, designed to block heat from the sun, Earth and Moon. Once deployed, this shield keeps Webb's instruments chilled to about 230 degrees, just a few degrees above absolute zero. The location, unlike Hubble, which orbits Earth, Webb was placed 1.5 million kilometers away at a point in space called Lagrange Point 2, L2. From here, it enjoys a stable environment with Earth, Moon and Sun always on the same side of its shield, leaving its mirrors facing deep space in eternal darkness. This vantage point minimizes interference and allows Webb to stay icy cold, watching the universe without the glow of Earth in its way. Each of these innovations represented a leap of engineering and a gamble. Unlike Hubble, Webb could never be serviced by astronauts. Once launched, it had to work perfectly. Thousands of scientists and engineers from NASA, ESA, and the Canadian Space Agency dedicated decades of effort to make sure of it. The power of Webb is not just in its mirror, but in the instruments it carries. NIRCam, near-infrared camera. Its main imager, capable of capturing breathtaking pictures of galaxies and moons alike, tuned to reveal light stretched into the infrared. NIRSpec, near-infrared spectrograph. An instrument that dissects light into its colors, showing the fingerprints of elements and molecules. With NIRSpec, scientists can tell what Europa's surface is made of: ice, salts, or carbon compounds. MIRI, mid-infrared instrument, extends Webb's reach further into the spectrum, capable of detecting cooler objects like dust, organic compounds, and subtle heat signatures. FGS, NIRI-S, fine guidance sensor, near-infrared imager, and slitless spectrograph, provides pinpoint accuracy for Webb's aim, while also performing specialized observations like spotting the tiny dimming of starlight as exoplanets pass by. Together, these instruments form a symphony of infrared vision, turning Webb into a machine that can not only see Europa, but analyze it molecule by molecule. The dream of Webb did not come easily. Its path was long, fraught with delays and budget overruns. Originally scheduled for launch in 2007, it was delayed by more than a decade. Critics doubted it would ever fly. Engineers wrestled with challenges: how to fold a mirror so large, how to design a sun shield that would deploy in space without tearing, how to ensure thousands of moving parts would all work perfectly. For a mission where a single jammed hinge or torn sheet could spell disaster, the risks were immense, but the stakes were higher still. Humanity needed Webb to work, not just for astronomy's sake, but for what it represented, a leap of faith in our own ability to solve the impossible. Finally, on December 25, 2021, Webb was launched aboard an Ariane 5 rocket from French Guiana. On Earth, millions watched as the telescope rose into the sky on Christmas morning, carrying with it decades of hope. Over the next month, it traveled to L2, unfolding its sun shield and mirror like a delicate origami flower. Step by step, everything worked flawlessly. When Webb sent back its first images in July 2022, deep fields of galaxies glittering like jewels, the world knew it had been worth the wait. At first glance, one might wonder why such an advanced telescope, designed to look back billions of years to the dawn of time, would turn its gaze to a moon in our own solar system. But Europa is exactly the kind of world where Webb's infrared vision shines. Europa's icy surface reflects sunlight in ways that mask its chemical secrets from telescopes limited to visible light. Infrared, however, penetrates deeper, revealing the spectral fingerprints of molecules within the ice. CO2, salts, sulfates, each leaves a unique signature. By analyzing the faint glow from Europa's surface, Webb can determine what compounds are present, where they are concentrated, and whether they may have come from the hidden ocean below. Even more, Webb's sensitivity allows it to search for plumes, geysers of water vapor that some scientists believe erupt from cracks in Europa's shell. If these plumes exist, Webb could detect the faint signatures of molecules in them, giving us a direct sample of the ocean without ever landing. But Webb is more than an instrument, it is the embodiment of human imagination. Each mirror segment, each gold coating, each carefully folded layer of its shield is the result of years of trial, error, and relentless pursuit of knowledge. It is a reminder that our species, bound to a small planet orbiting an ordinary star, has built a machine capable of reaching across space and time to answer questions once reserved for myth and speculation. And so when Webb turns its gaze to Europa, it is not just a telescope staring at a moon. It is humanity itself, our curiosity, our persistence, our hunger to know, reflected in golden mirrors floating 1.5 million kilometers away. Now that we understand the vision and power of Webb, we can return to the icy enigma of Europa. With its instruments trained on Jupiter's moon, Webb has begun peeling away the layers of ice and shadow. What it has seen, and what it has not seen, reshapes everything we thought we knew about this frozen world. When we think of the James Webb Space Telescope, we often imagine it as a time machine, peering back to the dawn of the universe, capturing light that has traveled for billions of years. Yet Webb is not just a window into the distant past. It is also a magnifying glass for our cosmic backyard. The same golden mirrors that can detect galaxies being born can also turn inward toward the planets and moons of our own solar system, offering a new perspective on worlds we thought we already knew. And among those worlds, few are more compelling than Europa. Europa has always been a difficult target. From Earth, it is nothing more than a point of light, drowned in the glare of Jupiter. Even the best ground-based telescopes struggle to isolate its faint reflections from the gas giant's brightness. Our atmosphere adds to the challenge. The very air that allows us to breathe blurs and absorbs infrared light, making it nearly impossible to see Europa's true chemical makeup from the ground. Astronomers can glimpse its icy surface, measure its albedo, the way it reflects sunlight, and infer some of its properties. But the deeper secrets, the fingerprints of molecules in the ice, remain hidden. Even Hubble, orbiting above Earth's atmosphere, was limited. Hubble's strength lay in ultraviolet and visible light. It captured stunning images of Europa's cracked face and even suggested tantalizing hints of water vapor plumes erupting into space. But it could not definitively tell us what Europa's surface was made of, nor could it reach into the infrared spectrum where the real answers lie. Infrared is the light of heat. It is emitted by every object that isn't at absolute zero. For scientists, this spectrum is a treasure chest of information. Molecules absorb and emit infrared radiation in unique ways. Water ice has one signature, carbon dioxide has another. Salts, organics, sulfates, each leaves a spectral fingerprint that can be identified if your telescope is sensitive enough. This is why Webb's infrared vision is revolutionary. Where Hubble could only scratch the surface, Webb can read Europa like a forensic investigator, decoding the composition of its ice and revealing whether its surface chemistry is linked to the hidden ocean below. The spacecraft that have flown past Jupiter, Voyager, Galileo, even Juno have provided invaluable data. Voyager gave us the first close-up glimpses. Galileo revealed Europa's magnetic anomalies and strong evidence for a salty subsurface ocean. Juno, currently orbiting Jupiter, has offered new views of the giant planet itself and some flybys of its moons. But none of these spacecraft carried the instruments Webb does. Their cameras and detectors were built for broader planetary science, not for the detailed chemical analysis that Webb can perform from afar. Where Galileo could measure magnetic fields, Webb can detect carbon dioxide molecules. Where Voyager could see surface cracks, Webb can determine what compounds lie within them. In a sense, Webb complements these missions. It does not replace them, but enhances their discoveries, adding a new dimension of understanding. Though designed to peer into the distant cosmos, Webb has already demonstrated its power closer to home. It captured detailed images of Neptune, revealing its rings more clearly than any telescope since Voyager 2 flew past in 1989. It observed Saturn's moon Titan, detecting clouds in its thick atmosphere. It studied asteroids in the Kuiper Belt, measuring their temperatures and surface compositions. And it turned its gaze toward Mars, despite the red planet's blinding brightness, detecting carbon dioxide in its thin atmosphere with unmatched clarity. Each of these observations proves the versatility of Webb. It is not limited to ancient galaxies or distant stars. It can also be a planetary scientist's tool, reshaping our understanding of familiar worlds. Among all the worlds Webb could observe, why Europa? The answer is simple: habitability. Of all the places in the solar system, Europa is one of the most likely to harbour life. Its ocean may contain twice as much water as Earth's, locked beneath an icy crust. The energy from tidal heating, the chemistry of salts and minerals, the possibility of hydrothermal vents, all suggest a world where life, at least microbial life, could find a foothold. For astrobiologists, Europa is a natural laboratory. If life exists in its dark seas, it would mean life can emerge in environments radically different from Earth. It would mean life is not an accident confined to one small planet, but a phenomenon written into the universe itself. Webb offers the chance to take the first real step toward answering that question. By studying Europa's surface, by analysing the chemistry of its ice and the possibility of plumes, Webb can tell us whether the building blocks of life, carbon, salts, organics, are present. But this is no easy feat. Webb was designed to look at faint galaxies billions of light years away, not bright objects within our solar system. Jupiter and its moons shine brightly in infrared, often too bright for Webb's ultra-sensitive instruments. To observe them, scientists had to adapt their methods, shortening exposures, narrowing their instruments' fields of view, and carefully calibrating the data to prevent overload. Think of it like trying to photograph a candle in the middle of a floodlight. You risk being blinded by the brightness. Yet Webb managed to balance this challenge, capturing data of extraordinary precision. When Webb turned its golden eye to Europa, scientists held their breath. For years, they had speculated about the chemistry of its surface. Was the carbon detected by earlier instruments delivered by meteorites, or did it come from the ocean below? Was there evidence of recent geological activity? Could Webb confirm or refute the existence of plumes? The answers, revealed in its first observations, would be groundbreaking. Webb detected not just water ice, but concentrated regions of carbon days. Dioxide on Europa's surface, a discovery that would soon reshape our understanding of the Moon's connection to its hidden ocean. For decades, Europa was a mystery painted in broad strokes. We knew it had ice, we suspected it had water, we dreamed it might have life. But Webb brought us closer than ever before, not with sweeping images, but with chemical signatures written into the ice itself. This was a turning point. Suddenly, Europa was not just a moon of possibility, but a world with evidence. Webb was not only confirming theories, but providing new ones, guiding the future missions, Europa, Clipper, and JUICE, to the most promising places. Now, with the challenge of observing Europa overcome, Webb's instruments revealed something extraordinary. Deep in the icy scars of Europa's surface, Webb detected the unmistakable fingerprint of carbon dioxide. And in doing so, it gave us the strongest evidence yet that Europa's hidden ocean may be far more Earth-like and far more alive than we ever dared to imagine. For decades, Europa had been a world of hints and shadows. Voyager showed us a smooth surface crisscrossed by scars. Galileo suggested a hidden ocean with its magnetic field data. Hubble teased us with possible plumes of water vapor. But none of these glimpses gave us certainty. They left us with questions, whispers of evidence, and the gnawing suspicion that something extraordinary lay beneath the ice. Then, in 2022, the James Webb Space Telescope turned its golden mirrors toward Jupiter's icy moon. For the first time, humanity's most powerful eye would attempt to read the fingerprints of Europa's chemistry, not through guesses or proxies, but directly, through light itself. Webb's secret weapon is spectroscopy, the ability to split light into its component wavelengths and read the unique signatures of molecules. Just as each element on Earth leaves a pattern in a rainbow, every compound in Europa's ice leaves a mark in the infrared. When Webb's near-infrared spectrograph, NIR-SPEC, studied Europa, it found those marks. Among them, one stood out above all, the clear signature of carbon dioxide. On Earth, carbon dioxide is everywhere, in our breath, in our atmosphere, in the fizz of oceans. But on Europa, it was not expected to be so concentrated. Even more striking, Webb revealed that the carbon dioxide was not scattered randomly. It was clustered in a specific region, Terra Regio. Terra Regio is one of Europa's most enigmatic features. Known as a chaos terrain, it is a jumbled patchwork of broken ice, ridges, and disrupted surface. Imagine a landscape where the crust has been shattered and refrozen, where blocks of ice the size of cities float like puzzle pieces in a frozen sea. This terrain is geologically young, reshaped in the recent past, perhaps only a few tens of millions of years ago, a blink in planetary time. The presence of concentrated carbon dioxide here suggested something profound. The surface and the subsurface might be connected. Carbon dioxide is fragile on Europa's surface. Radiation from Jupiter's magnetosphere should destroy it quickly. Its very presence implies it is being replenished, and the most likely source is from below. The discovery ignited excitement across the scientific community. If the carbon dioxide came from the ocean, it meant that Europa's hidden sea is not sealed off forever. Instead, materials may cycle between the depths and the surface. Cracks in the ice, eruptions, or convective movement could carry ocean chemistry upward, depositing it in places like Terra Regio. This matters because carbon is the backbone of biology. Without carbon, life as we know it cannot exist. Detecting carbon dioxide does not prove life, but it proves that Europa's ocean contains the ingredients life requires. It is as if Webb had lifted a corner of Europa's icy blanket and whispered, "Yes, there is carbon here. Yes, the ocean on myself," and speaks through the ice. For years, Hubble data had hinted at possible plumes, geysers of water vapor erupting into space, much like those seen on Saturn's moon Enceladus. If true, they would provide a direct window into the ocean, a way to sample it without drilling. Webb looked for plumes. It searched for excess water vapor in Europa's thin atmosphere, but it found none. This non-detection does not disprove the plumes. They may be intermittent, erupting only occasionally. They may be smaller or weaker than we thought, or they may exist in places Webb has not yet observed. Still, the absence was sobering. For now, there is no smoking gun, no fountain spraying ocean water into space. Europa remains guarded, its secrets mostly locked away. In addition to carbon dioxide, Webb's instruments also provided hints about the salts in Europa's ice. These salts, sodium chloride, sulfates, carbonates, are clues to the chemistry of the ocean below. Each type of salt tells a different story. Sulfates suggest volcanic activity. Chlorides suggest an ocean more like Earth's seawater. Though Webb's results are still being refined, the evidence points toward an ocean that is complex, chemically diverse, and capable of supporting reactions that life would need. The ice itself, too, tells a story. Its texture and reflectivity suggest a surface shaped not just by impacts, but by active geological processes. Europa is not a frozen rock, but a dynamic world, constantly reshaping itself, carrying whispers from the deep up to the surface. The detection of carbon dioxide concentrated at Terra Regio is more than a chemical result. It is a milestone. It confirms that Europa's ocean is communicating with the surface. It proves that the carbon cycle, a fundamental process for life, exists on a moon 500 million miles from Earth. In astrobiology, this is a game changer. Until now, Europa was a hypothesis, an ocean world that might possibly contain the conditions for life. Now, with Webb's data, we know its ocean is not just water, but chemically active, enriched with carbon. Science, however, thrives on skepticism. Not all are convinced that the carbon dioxide comes directly from the ocean. Some argue it could be produced on the surface by radiation breaking down other carbon-bearing compounds. Others suggest it may have been delivered by comets or asteroids. But the concentration at Terra Regio, the freshness of the terrain, and the instability of carbon dioxide under Europa's conditions all point strongly toward an internal source. The debate will continue, but Webb has shifted the balance of evidence in favor of an oceanic origin. For the public, the discovery rekindled fascination. Headlines declared Europa a candidate for life. Scientists compared it to Earth's deep oceans. For a moment, the icy moon was no longer just a distant world orbiting Jupiter, but a mirror of possibility, a reminder that Earth might not be the only cradle of biology in our solar system. And yet, even as Webb revealed these secrets, it deepened the mystery. Europa is still silent. It offers no clear proof of life, no obvious signs of biology. Instead, it tempts us with evidence of habitability, a world that has everything life needs, if only life ever managed to spark there. But where exactly did Webb see this carbon? What makes Terra Regio such a special place on Europa's surface? To understand the true significance of this discovery, we must journey into the strange and chaotic landscapes of Europa's fractured shell, places where the ice is broken, churned, and perhaps connected to the sea below. When James Webb revealed that carbon dioxide was concentrated in Terra Regio, scientists weren't just surprised, they were electrified. This was no random patch of Europa's surface. Terra Regio is one of the most geologically intriguing regions on the Moon, a place where the ice shell itself seems to have shattered, refrozen, and churned like a broken mosaic. If there is any spot on Europa that whispers of a connection to the ocean below, Terra Regio is it. Europa's chaos terrain is unlike anything else in the solar system. Imagine looking down from orbit. Instead of smooth plains or craters, you see a surface that looks shattered, as if the crust has been smashed into giant blocks, tilted, rotated, and jumbled together. Between these blocks lies refrozen slush, filling gaps with fresh, bright ice. Geologists call this pattern chaos terrain. Tara Regio is one of the largest and most famous examples, sprawling for thousands of square kilometers. To some, it looks like a battlefield of ice. To others, it resembles Arctic pack ice that has broken, drifted, and refrozen. The important thing is this: chaos terrain is young. Compared to Europa's smoother plains, it is geologically fresh, meaning something in Europa's recent past has disturbed it. That something may well be the ocean. Scientists have debated for decades how chaos terrain forms. Several theories compete, each with evidence in its favor. Surface collapse, over melt pockets. Some believe chaos terrain forms when parts of the ice shell collapse into subsurface lakes or melt pockets. As the ice melts and refreezes, it disrupts the crust, shoving blocks around like fractured glass. Diapirs. Rising from below, others suggest warmer, softer ice rises up from below, like blobs of wax in a lava lamp. These diapirs push through the colder, brittle crust, breaking it apart. Direct ocean connection, the most exciting. An possibility is that chaos terrains are places where the ocean and surface meet. Cracks may open all the way down, allowing salty ocean material to rise and spill onto the surface, then refreeze. Whichever model is correct, and it may be a combination, chaos terrain represents activity. It is Europa in motion. It's ice, not a static shell, but a dynamic system connected to the depths. Of all Europa's chaos terrains, Tara Regio stands out. Not only is it large and geologically young, but Webb's discovery placed carbon dioxide directly within it. This is crucial. If the CO2 was spread evenly across Europa, scientists could argue it came from external sources, comets, meteorites, or radiation chemistry. But its concentration in a geologically active chaos terrain strongly suggests an internal origin. The carbon is not falling from the sky, it is rising from the sea. In other words, Tara Regio may be one of the few places where Europa's ocean has expressed itself on the surface, a chemical fingerprint of the deep left behind in ice for Webb to read. Carbon dioxide is not stable on Europa's surface. Jupiter's intense radiation bombards the Moon constantly, breaking down fragile molecules in relatively short timescales. That means the CO2 Webb detected cannot have been sitting on the ice for millions of years. It must be recent. And if it is recent, it must be replenished. The simplest explanation is that CO2 was delivered upward from the subsurface ocean or a shallow reservoir beneath Tara Regio. This points directly to surface-ocean exchange, one of the key requirements for habitability. Think of Tara Regio as a window, not an open window, but a frosted, cracked pane through which we glimpse shadows of the ocean below. If the carbon dioxide there is indeed oceanic, then by studying this region, we are indirectly sampling Europa's sea without ever drilling through the ice. This has profound implications for future missions. NASA's Europa Clipper spacecraft, launching later this decade, is designed to perform dozens of flybys of Europa. Webb's discovery at Tara Regio tells Clipper exactly where to look. If Clipper's instruments can confirm salts, organics, or other carbon compounds in this region, we may one day hold the chemical recipe of an alien ocean in our hands. Chaos terrains may also be more than windows. They may be crucibles. The mixing of ice, salts, and ocean material could create chemical gradients, the kind of energy sources life thrives on. On Earth, hydrothermal vents at the seafloor produce similar gradients, fueling ecosystems of bacteria, worms, and crustaceans. Could Europa's chaos terrains represent the icy analogue of such environments where energy and chemistry collide? If so, Tara Regio may not just record the conditions for life, it may hint at places where life could exist right now. Of course, as with all great discoveries, debate rages. Some scientists argue that the CO2 might still be formed on the surface, perhaps by radiation altering other carbon-bearing compounds. Others suggest comets could have delivered the material, later concentrated by surface processes. But the geological youth of Tara Regio and the instability of carbon dioxide under Europa's conditions make the internal explanation the most compelling. Webb has not closed the case, but it has given us the most persuasive evidence yet. Visually, Tara Regio is haunting. If you stood there, you would see towering blocks of ice, some tilted, some upright like ozone monuments. Between them, smooth plains of refrozen slush would gleam under Jupiter's faint sunlight. The ground beneath you would be uneven, fractured, alive with the memory of upheaval. And beneath your feet, perhaps only a few kilometers down, an ocean deeper than Earth's, pressing upward, whispering through cracks. The carbon dioxide Webb detected might have risen through those cracks, carried in brine, then frozen into the surface for us to see. Europa's broken beauty is not a flaw, it is a feature, a sign that this world is active, dynamic, and potentially habitable. But if Tara Reggio gives us a window into the ocean, what about the plumes, those spectacular geysers once hinted at by Hubble? Could Europa, like Saturn's Enceladus, be spraying its secrets into space? Webb searched for answers, and what it found and did not find may change how we hunt for life on this icy moon. For scientists studying Europa, one dream has always burned brighter than the rest: the possibility of plumes, great geysers of water erupting through cracks in the ice, spraying ocean material directly into space. If such plumes exist, they would offer a shortcut past Europa's greatest obstacle, its kilometers-thick shell of ice. Instead of drilling, we could simply fly through the spray, tasting the chemistry of the ocean without ever touching the surface. Saturn's moon Enceladus has made this dream feel possible. When the Cassini spacecraft flew past Enceladus, it discovered towering jets shooting from fissures in the South Pole, plumes filled with salty water, organic compounds, even molecular hydrogen. Cassini's instruments were able to sniff those plumes, giving scientists a direct sample of an alien ocean. The result was electrifying. Enceladus is now considered one of the most promising habitats for life beyond Earth. Could Europa do the same? The first clues came not from a spacecraft orbiting Jupiter, but from the Hubble Space Telescope. In 2012, Hubble observed faint ultraviolet emissions near Europa, consistent with water vapor. Later observations in 2016 showed similar signs. These hints suggested possible plumes rising hundreds of kilometers above the surface. The prospect was thrilling. If Europa had plumes, missions like NASA's planned Europa Clipper could fly directly through them, sampling ocean material in real time. Suddenly, Europa seemed like a twin to Enceladus, an ocean world speaking through geysers. But Hubble's data was limited. The signals were faint, barely above detection limits. Some scientists argued the features could be explained by instrumental noise or background contamination. Others believed the plumes might exist but erupt sporadically, making them difficult to catch in the act. Europa had given us a tantalizing tease, but no clear confirmation. When the James Webb Space Telescope was launched, plume detection became one of its top priorities for Europa. Webb's infrared instruments are capable of detecting water vapor, carbon dioxide, and other molecules in faint quantities. If plumes were erupting, Webb should be able to see them with greater clarity than Hubble ever could. And so, scientists aimed Webb at Europa, searching for telltale signatures, extra water vapor in the thin atmosphere, hotspots of infrared emission, or direct images of sprays against the blackness of space. The world held its breath. What Webb found was, in a sense, nothing. There were no towering fountains, no extra water vapor, no clear signs of plumes. The instruments, sensitive enough to detect faint chemistry across Europa's surface, saw no active jets during the observation window. For some, this was a disappointment. Decades of speculation about Europa's geysers seemed to collapse in silence. Perhaps the plumes never existed at all. But science thrives in nuance. Webb's non-detection does not mean plumes are impossible. It simply means none were active when Webb looked. Europa, unlike Enceladus, may not have continuous jets. Its plumes might be intermittent, eruptions triggered by tidal stresses as the moon orbits Jupiter, or localized bursts that last only hours or days. In other words, Webb may have just looked at the wrong time. Europa's orbit is elliptical, meaning its distance from Jupiter varies slightly. This creates tidal stresses that flex and heat the ice shell. On Earth, tidal forces move oceans and trigger geological activity. On Europa, they may occasionally crack the ice, releasing bursts of water vapor. If this is true, Europa's plumes may erupt on a schedule tied to its orbit, or they may be unpredictable, like geysers in Yellowstone, bursting suddenly and then falling silent for months or years. Catching such an eruption requires luck or sustained monitoring. Hubble's detections may have been fortunate snapshots of brief events. Webb's silence may simply mean the geysers were sleeping. Even without seeing plumes, Webb's data is invaluable. It places limits on how strong Europa's plumes can be. If geysers do exist, they are not massive, constant jets like Enceladus. They are smaller, rarer, or less powerful. This distinction matters. It suggests Europa is more guarded, its ocean less willing to reveal itself. It reminds us that each icy moon is unique, shaped by different histories, different geologies, different balances of heat and pressure, and yet Europa still holds an advantage. Even if plumes are rare, they only need to exist occasionally. Future spacecraft, especially Europa Clipper, can try again and again, watching for the right moment. With dozens of planned flybys, the odds of catching an eruption increase. Webb has narrowed the mystery, but it has not closed the case. Webb's silence on plumes also highlights the importance of complementary missions. A space telescope can reveal chemistry and atmospheric signatures, but a dedicated orbiter can linger, waiting, listening, circling until Europa finally reveals its breath. For now, what we know is this: Europa is not Enceladus. It does not spray its secrets continuously into the void, but it may still whisper them, rarely and briefly. Our challenge is to be listening when it does. There is also a deeper lesson here, that absence is itself data. The non-detection tells us about Europa's behavior, its geologic rhythm, its hidden dynamics. Science advances not only through discoveries, but also through constraints. By learning what is not happening, we sharpen our sense of what could happen and why. In this way, Webb has not dashed our hopes. It has refined them. It has told us, do not expect fountains in the sky, expect subtler signs, rarer events. And in doing so, it has guided us to be more precise, more patient, more deliberate. There is a poetic irony here. For years, Europa has been imagined as a world eager to reveal itself, spraying plumes into space like cosmic beacons. Instead, Webb shows us a quieter moon, reluctant, secretive, forcing us to work harder for answers. Perhaps this is fitting. If Europa's ocean does hold life, it would not give it up easily. The silence may not be a denial, but a challenge to invent better tools, to build bolder missions, to keep looking until we understand. Yet even without plumes, Webb's detection of carbon dioxide at Tara Regio carries enormous implications. For life to exist, an ocean needs more than water. It needs carbon, energy, and chemistry. In its search, Webb has shown us that Europa's ocean may indeed carry the ingredients of biology. And so, the question grows sharper. Does Europa simply have the conditions for life, or does something already swim in its dark sea? For all the marvels of Europa, its icy plains, its fractured chaos, its potential plumes, one element matters most of all: carbon. Life as we know it is a carbon-based phenomenon. From the DNA in our cells to the sugars that fuel us, from the shells of microbes to the vast forests of Earth, all life depends on carbon's extraordinary ability to form bonds, to build complex molecules, to create chemistry flexible enough to spark biology. And this is why Webb's discovery of carbon dioxide on Europa was so electrifying, because in that one chemical fingerprint, the telescope did more than detect a gas. It pointed to the possibility that Europa's hidden ocean has the fundamental ingredient life requires. Carbon is sometimes called the backbone of biology. Unlike most elements, it can bond with itself and with many others in endless combinations: chains, rings, lattices, branching molecules. This versatility allows for the creation of proteins, lipids, carbohydrates, and nucleic acids, the building blocks of organisms. On Earth, carbon cycles through the planet. From volcanic emissions into the atmosphere, into oceans where it dissolves as carbonates, into rocks where it is stored, and into living things where it forms the architecture of cells. Without this cycle, Earth would be sterile. So when Webb revealed carbon dioxide concentrated at Tara Regio, scientists saw more than a frozen gas. They saw evidence that Europa's ocean participates in a cycle of its own. If carbon is rising to the surface, then it must exist in the sea. And if it exists in the sea, then the ocean is not simply water, it is chemically active. Astrobiologists often describe three main ingredients for habitability. Liquid water. Europa has it in abundance, likely more than all of Earth's oceans combined. Energy sources, tidal heating, and possible hydrothermal vents could provide the energy tissue. Fuel chemical reactions, essential chemistry, carbon, nitrogen, phosphorus, sulfur, and trace metals, which together allow life's molecules to form. Until Webb's discovery, the third ingredient was uncertain. We knew there was water. We knew tidal forces generated heat, but without carbon, the ocean might be sterile. Now, with evidence of carbon dioxide linked to ocean exchange, the trifecta feels complete. To imagine what Europa's ocean might be like, scientists look to Earth's own extremes. Deep beneath the surface, far from sunlight, lie hydrothermal vents along mid-ocean ridges. There, superheated water rich in minerals bursts from the seafloor, creating an ecosystem that thrives without light. Tube worms, crabs, and bacteria live off the chemical energy alone, using a process called chemosynthesis instead of photosynthesis. This discovery, first made in 1977, changed biology forever. It proved that life does not require sunlight. It requires only water, chemistry, and energy. And suddenly, places like Europa no longer seemed impossible. If life can flourish in the abyss of Earth, why not in the abyss of a moon? But life is more than water and heat. It is chemistry. The carbon dioxide detected by Webb could play many roles. It might dissolve into Europa's ocean as carbonic acid, altering the water's chemistry. It could combine with minerals on the ocean floor, creating carbonates that store carbon long term. It might even provide raw material for microbes, if they exist, to build organic molecules. In fact, some scientists argue that carbon dioxide is a necessary precursor to biology. Without it, the ocean would lack the raw feedstock for complexity. Its presence means Europa's ocean is not inert. It is active, dynamic, and, at least chemically, alive. There is a caution here. Just because carbon dioxide is present does not mean biology is inevitable. The ocean may still be sterile, its chemistry rich but uninhabited. Yet even that possibility is extraordinary, because studying a sterile ocean world teaches us just as much as finding life. It tells us what the limits are, what conditions fail to spark biology, what ingredients are necessary but not sufficient. And then there is the deeper mystery. What if life in Europa's ocean does not follow Earth's rules? What if it uses carbon in ways we cannot yet imagine? Life may not mirror our biology perfectly, but carbon's versatility makes it the best candidate to support something recognizable as living. At Saturn's moon Enceladus, Cassini found not only plumes of water, but also organic molecules, hydrogen and salts, a chemical soup astonishingly similar to Earth's oceans. Enceladus showed us that icy moons can host all the necessary conditions. Europa, larger and more geologically active, could be even richer. The detection of carbon dioxide suggests its ocean may rival Enceladus in potential, but where Enceladus sprays its chemistry into space, Europa holds its secrets tighter, revealing them only through the fractured terrains Webb has now probed. If Europa has carbon, water, and energy, then the question sharpens: why not life? The universe has provided the stage, the props, the chemistry. Is it really possible that nothing took the final step? This question goes beyond science. It touches on philosophy, on our sense of uniqueness. If life exists in Europa's ocean, then life is not rare. It is common, inevitable, written into the laws of physics and chemistry. And if it does not exist there, even with all the right conditions, then perhaps life is rarer than we imagine, a fragile spark unique to Earth. Either answer is profound. Either reshapes how we see ourselves. For now, Webb's discovery is a clue, not a conclusion. It tells us carbon is present. It suggests an ocean-ocean exchange. It strengthens the case for habitability, but it does not tell us whether anything swims in the dark. That answer must wait for future missions, perhaps even landers that can one day sample the ice directly. Still, humanity dreams. Scientists sketch models of Europa's ecosystem, bacteria feeding on chemical gradients, colonies near hydrothermal vents, strange multicellular organisms drifting in the black waters. Artists imagine bioluminescent creatures glowing beneath the ice, and all of it, every story, every hope, begins with carbon. Yet Europa is not alone. It is only one of many icy moons orbiting the giants of our solar system. Ganymede, Callisto, Titan, Enceladus, each hold secrets of water, chemistry, and potential. To truly understand Europa, we must see it in context, as part of a family of ocean worlds, where Webb's vision is only beginning to reveal the possibilities. Europa may be the star of this story, but it is not alone. Across the solar system, scattered around gas giants and drifting in the darkness, lies a family of worlds that may also cradle hidden oceans. They are icy, distant, and seemingly barren, yet beneath their frozen shells, they may hold the same promise that makes Europa so compelling. The James Webb Space Telescope was built to study the early universe, but it is also beginning to cast its gaze on these other moons, comparing their chemistry, their geology, and their potential. To understand Europa fully, we must see it in this context, as one among many ocean worlds where nature has written the same script in different variations. Orbiting alongside Europa is Ganymede, the largest moon in the solar system, even bigger than Mercury. Where Europa is mysterious and smooth, Ganymede is scarred and ancient, with regions of bright and dark terrain telling a story of billions of years of change. Like Europa, Ganymede is believed to have a deep ocean beneath its icy crust. In fact, models suggest multiple stacked layers of water and ice, perhaps more complex than Europa's single sea. If true, this ocean could be hundreds of kilometers deep. In 2022, Webb observed Ganymede's surface, detecting signs of frost, ice, and complex molecules. Though less famous than Europa, Ganymede's sheer size and magnetic field, the only moon in the solar system to generate one, make it fascinating. It may shield its ocean from some of Jupiter's harsh radiation, creating more stable conditions for habitability. But there is a challenge. Ganymede's ocean may be trapped between high-pressure ice layers, isolated from the rocky mantle below. If so, the ocean could lack the mineral interaction that makes Europa's sea potentially so rich. Life needs more than water. It needs chemistry. For Ganymede, the jury is still out. Farther out, Orbi, it's Callisto, a battered world covered in craters, its surface among the oldest in the solar system. At first glance, Callisto looks dead, frozen, unchanging, a relic of the early solar system. Yet even Callisto may harbor a subsurface ocean. Magnetic measurements by Galileo hinted at conductive material beneath the crust, possibly a salty sea. Unlike Europa or Ganymede, Callisto shows little geological activity. If its ocean exists, it may be locked away, stagnant, untouched for billions of years. Webb's early observations of Callisto revealed subtle signs of surface ice mixed with darker material, perhaps organics delivered by comets. Callisto may not be the most promising home for life, but it remains a scientific treasure. By studying it, we glimpse a world that has preserved the scars of solar system history, a frozen archive of ancient impacts and chemistry. If Europa is a mystery, Enceladus is a revelation. This tiny moon of Saturn, only 500 kilometers across, stunned the world when Cassini discovered plumes blasting from fissures at its south pole. These jets, shooting hundreds of kilometers into space, carry water vapor, salts, and organic molecules from a global ocean beneath the ice. Enceladus gives us what Europa has withheld, a direct sample of its sea. Cassini flew through the plumes, analyzing their chemistry, finding hydrogen gas, a potential energy source for microbes, and complex organics that hinted at prebiotic chemistry. Webb has begun to turn its instruments toward Enceladus as well, confirming water vapor in the plumes and detecting more chemistry in their glow. For many scientists, Enceladus is already a world of habitability. Its ocean is accessible, its plumes a natural laboratory. The next step is to ask not just whether the conditions are right, but whether life is already there. Among Saturn's moons lies another enigma, Titan. Larger than Mercury, Titan has a thick nitrogen atmosphere, lakes of methane and ethane, and a complex surface where rivers of liquid hydrocarbons carve channels into icy plains. Beneath its crust of water ice, Titan too may hide an internal ocean of liquid water mixed with ammonia. Unlike Europa or Enceladus, Titan is not simply a water world, it is a hybrid, with both hydrocarbon chemistry on the surface and a water ocean below. Webb's infrared vision has already pierced Titan's thick haze, mapping its atmosphere and detecting clouds drifting across its skies. Titan is not just a frozen moon, it is dynamic, weathered by methane rains and hydrocarbon cycles eerily parallel to Earth's hydrological system. If Europa represents one path to habitability, a salty ocean beneath ice, Titan represents another stranger possibility, life based not on water at all but on methane. Though speculative, Titan reminds us that life may not always look like what we know. Europa, Ganymede, Callisto, Enceladus, Titan. Together they form a family of ocean worlds, each different, each a natural experiment in planetary chemistry. Some are geologically active, some are ancient and quiet. Some exchange their oceans with the surface, others may bury them under layers of ice. For astrobiologists, they are all test cases. If life exists on one, it suggests life could exist on others. If life does not exist on any, then perhaps water and carbon alone are not enough. Webb's role in this family is to provide the first comparisons. By analysing their spectra, mapping their chemistry, and detecting their ices and vapours, Webb gives us the data to ask deeper questions. Which worlds are chemically active? Which oceans connect to their surfaces? Which are worth sending spacecraft to explore next? Seen in this light, Europa is no longer just a sign. Nulla hope. It is part of a pattern, a cosmic chorus. The solar system may be dotted with more oceans than dry surfaces. Earth's seas are not unique, they are one of many. The universe, it seems, loves to make water worlds. And so when Webb detected carbon dioxide at Europa, it was not just a discovery about one moon. It was evidence that the pattern holds, that the conditions for habitability may be common, not rare, scattered across the icy moons of giant planets. But while Webb reveals the chemistry from afar, the next great leap will come from spacecraft that can get closer. NASA's Europa Clipper and ESA's JUICE mission are preparing to launch, guided by Webb's discoveries, ready to fly past these icy worlds again and again. If Webb has shown us where to look, these missions may show us what is truly there. The James Webb Space Telescope has given us tantalizing glimpses of Europa's chemistry, showing us that carbon dioxide exists in its chaos terrains, that the ocean may exchange material with the surface, and that plumes are at best elusive. But Webb cannot do everything. It cannot orbit Europa, it cannot map its surface in detail over years, and it cannot fly through the icy moon's atmosphere. For that, humanity must send dedicated explorers, spacecraft designed to dive deep into Europa's mysteries. And that is exactly what is coming. Two great missions, one American and one European, are on their way to the Jovian system. NASA's Europa Clipper and the European Space Agency's JUICE, Jupiter Icy Moons Explorer. Together, they represent the next great leap in our search for life beyond Earth. In 2024, NASA will launch the Europa Clipper, the most ambitious mission ever sent to study an icy moon. Its destination, Europa, the world Webb has just shown us in infrared detail. Unlike Galileo, which orbited Jupiter and made only a handful of flybys, Clipper is designed for precision. It will enter orbit around Jupiter and make nearly 50 close passes of Europa, each time diving just tens of kilometers above the surface. From these repeated encounters, Clipper will build a global map of the moon, covering geology, composition, atmosphere, and even subsurface structure. Clipper's instruments are formidable. EIS, Europa Imaging System, a high-resolution camera to map Europa's fractured surface in unprecedented detail. MIA-C, Mapping Imaging Spectrometer, to study the chemistry of the ice, detecting salts, organics, and minerals. REASON, Radar for Europa assessment and sounding, ocean to near surface. An ice-penetrating radar capable of probing through kilometers of crust to detect liquid reservoirs or the ocean beneath. SUDA, Surface Dust Analyzer, to study tiny particelles, clees ejected from Europa's surface, perhaps even material from plumes. MASSPEX, Mass Spectrometer for Planetary Exploration, to analyze Europa's thin atmosphere, searching for molecules that could reveal ocean chemistry. If Webb is the eye that glimpses from afar, Clipper will be the hand that reaches closer, touching Europa with its sensors, tasting its atmosphere, mapping its scars, and perhaps confirming whether its ocean is habitable. Webb's discoveries are already shaping Clipper's mission plan. By detecting carbon dioxide concentrated at Tara Regio, Webb has highlighted specific regions of interest. Clipper can target these sites for close study, flying over chaos terrains to search for signs of recent resurfacing or chemical exchange. The non-detection of plumes by Webb is also critical. It suggests plumes are rare, but not impossible. Clipper's strategy will be to monitor repeatedly, increasing the chance of catching one in action. If a plume is found, Clipper's instruments can fly through it, just as Cassini did at Enceladus. In this way, Webb acts as a scout, narrowing the field, pointing the way, ensuring that Clipper spends its precious time and energy in the most promising places. At nearly the same time, the European Space Agency has launched JUICE, Jupiter Icy Moons Explorer, which began its journey in 2023 and will arrive at Jupiter in the early 2030s. Unlike Clipper, which focuses almost exclusively on Europa, JUICE has a broader mandate to explore Ganymede, Callisto, and Europa as a system of icy worlds. It will perform multiple flybys of Europa, but ultimately settle into orbit around Ganymede, the first spacecraft ever to orbit a moon other than Earth's. JUICE's goals are complementary to Clipper's. It will study how these moons interact with Jupiter's massive magnetosphere, how their surfaces evolve, and whether their oceans might be habitable. By focusing on Ganymede, JUICE provides a comparison point showing us what makes Europa unique and what it shares with its siblings. The twin missions, Clipper and JUICE, represent something larger than individual agencies. They show a global commitment to exploring the ocean worlds of the outer solar system. NASA and ESA are not working in isolation. Their data will be shared, compared, and combined. Together, these spacecraft will provide a comprehensive view of Jupiter's moons, each filling gaps the other cannot, and all of it builds on the foundation Webb has laid. The telescope's infrared discoveries will help calibrate the instruments, focus the investigations, and frame the scientific questions the missions must answer. The timelines are long. Europa Clipper will not arrive at Jupiter until around 2030. JUICE, traveling on a slower trajectory, will not reach until 2031-2032. By then, Webb will still be operating, providing complementary data from afar. For at least a decade, humanity will be in the midst of a coordinated assault on the mysteries of the Jovian system, with telescopes above Earth and spacecraft among the moons. For the scientists who have spent careers waiting for this, the coming decades represent the payoff of generations of work. And for the rest of us, they represent the chance, perhaps the first real chance, to answer the question, are we alone? Why invest billions, wait decades, risk so much? Because the stakes are cosmic. If Europa or Ganymede or Enceladus harbors even microbial life, it would mean that life is not unique to Earth. It would mean that biology is a universal phenomenon, a natural outcome of water and chemistry. And if these oceans are sterile, then that too is profound. It would tell us that life is far rarer, that even with water, carbon and energy, biology does not spark easily. Either answer reshapes humanity's understanding of its place in the universe. In this context, Webb serves as the bridge. It cannot land, it cannot drill, it cannot sample directly, but it can see, it can guide, it can tell us where the chemistry lies, where the mysteries cluster, where the future spacecraft should look. In Tara Regio, Webb has given Clipper its first target. In the silence of the plumes, it has set the stage for patient monitoring. In the detection of carbon dioxide, it has raised the stakes for every future encounter. Webb is the scout on the frontier, shining a golden light into the darkness, preparing the way for the explorers to follow. And so as Clipper and JUICE prepare to take flight, we find ourselves at the edge of revelation. Europa has shown us its carbon. The ocean whispers through the ice, the plumes remain elusive. But the question grows sharper with every observation, every discovery. If the conditions for life exist, is life truly there? The final chapter of Europa's story is not just about one moon, but about humanity's oldest question. Are we alone in the universe? For all the data, all the chemistry, all the engineering marvels, the story of Europa is not just about science, it is about us, about what it means to be human, to look into the darkness of the cosmos and wonder whether we are unique or part of something larger. When the James Webb Space Telescope turned its golden eye toward Europa, it was not simply measuring spectra, it was asking, on behalf of all of us, are we alone? Europa's icy crust stretches across a world smaller than our moon, orbiting a planet we cannot see with the naked eye. Yet somehow this distant moon has become the stage for one of the most profound experiments in human history. Because Europa represents possibility, its global ocean, its chemistry, its energy sources, all of it converges into a single, staggering truth. Here, beyond Earth, the universe has written the script for habitability. Whether life has followed that script is the mystery Webb and the missions to come are trying to unravel. For decades, we have searched for signals of life. We have scanned the skies for radio messages, probed Mars for fossils, analyzed meteorites for organic compounds, yet the universe remains silent. Europa offers a different kind of test, not a search for alien civilizations, but for alien cells. For microbes, bacteria, or simple life forms that prove biology is not unique to Earth. The silence so far makes the stakes even higher. If we find life on Europa, even the simplest microbes, it means life emerges wherever it can. It means the galaxy is full of living worlds. But if we do not, then perhaps Earth is rarer, lonelier, more fragile than we dare admit. Webb's detection of carbon dioxide at Tara Regio is small compared to those vast questions, but it is also monumental. It tells us that carbon, the foundation of biology, exists where the ocean meets the surface. It tells us that Europa is not a seal-ed world, but one that exchanges and breathes. In science, we rarely get answers in leaps. We get them in steps. Webb's discovery is one such step, pointing us closer to the truth. It is a reminder that even silence, even uncertainty, is data that sharpens the question. In a way, Europa is a mirror. Beneath its frozen surface, it hides an ocean, dark, cold, and perhaps alive. When we study it, we are not just studying a moon, we are studying ourselves. We are asking, is life inevitable when conditions are right? Or is it an accident, a rare flame that flickers only once in a galaxy? Philosophers have long debated humanity's place in the cosmos. From ancient myths to modern science fiction, we have dreamed of other worlds, other beings. Now, for the first time, we are on the brink of finding out. NASA's Europa Clipper and ESA's JUICE will arrive in the 2030s. They will map, probe, and analyze. Perhaps they will confirm what Webb has hinted at. Perhaps they will even find organics, salts, or plumes that carry the unmistakable signs of biology. Beyond them, we imagine landers, spacecraft that could touch the ice, drill, or even melt down into the sea. Someday, perhaps centuries from now, humans themselves may walk across Europa's gleaming plains, gazing at Jupiter rising in the sky, drilling down to taste the waters of another world. The journey is long, but it has already begun. What compels us to spend billions, to wait decades, to build telescopes and spacecraft that may fail in the void? It is not survival, it is not profit, it is curiosity. The same drive that made our ancestors look up at the stars and wonder has now built machines that can answer those questions. The James Webb Space Telescope, orbiting far beyond the moon, is not just a tool of science, it is a monument to human imagination, proof that we are a species willing to dream bigger than ourselves. When it peers at Europa, it is not just a telescope looking at a moon, it is humanity asking a question older than civilization. If we find life on Europa, even microbial, it will change how we see the universe. It will no longer be life on Earth. It will be life in the cosmos. Religion, philosophy, science, all will be transformed by the knowledge that biology is not unique, that creation is wider, richer, stranger than we imagined. If we do not find life, the lesson is no less profound. It will mean Earth is rarer, more precious, perhaps the only oasis in a desert of stars. It will mean our duty to protect this planet, its forests, its oceans, its fragile balance is even greater, for it may be the only cradle of life the cosmos has produced. Either way, the answer will define us. And so as Webb peers into the darkness, as Clipper prepares to fly, as JUICE sails on its long journey, we are left with wonder. A frozen moon of Jupiter, cracked and scarred, hiding an ocean deeper than Earth's, may hold the key to our greatest question. The universe has given us the conditions. The rest is up to us, to build, to explore, to ask. Europa waits. When the James Webb Space Telescope detected carbon dioxide on Europa, it was more than a scientific result. It was a signal that the question of life is not abstract, not distant, but close within our reach. A moon orbiting Jupiter may hold the answer to humanity's oldest dream. Are we alone? Soon, perhaps, Europa will tell us.